So welcome everybody. Today we have Umut Varolgüneş from Stanford University in Üçgen, and he's going to tell us a little bit about homological mirror symmetry, in particular for chain type invertible polynomials.
Okay, thank you. Thank you for inviting me. Yeah, so I said in my abstract that I'm first going to introduce Picard-Lefschetz theory and then talk about the conjecture, but then I switched that around. So I'm going to first introduce the mirror symmetry conjecture relevant for this chain type polynomials, and then in the middle I'm going to say something about kind of basic notions of Picard-Lefschetz theory. Okay. So notation that's going to be fixed throughout the talk is A. Little a is going to be, maybe I should use a pointer actually. 1 second. Okay. It's visible, right? The pointer?
Yes.
So A throughout the talk, A will be just a vector of integers, positive integers. In fact, there are going to be at least 2. Okay, so this is some kind of technical assumption. And let me not discuss why I'm making this assumption. You could discuss the remaining cases when the integers are 1 or 0 if you want. 0 is easy, but 1 is not. It's a special case. Okay, so for given such a vector of integers, we define this chain type polynomial. So if the vector has n entries, it's a polynomial in n variables. And it's defined in this way. And P sub A will just say, it will signify that this P is the polynomial associated to A. And so it just goes, and the reason why it's called chain type is because the variables are kind of linked to each other in the manner of a chain. So let me, for example, do, if n is equal to 1, x to the 5 could be an example. When n is equal to 2, x squared y plus y to the 7 could be an example. If n equals 3, then x cubed y plus y cubed z plus z cubed is an example, and so on. You can see how it's going. So there's the first variable. You take its exponent to some integer, multiply it by the second one. Take the second one, take its exponent to the given integer, the second integer in the vector, multiply with the third one, and so on. And when you get to the very end, you don't have an n plus first integer, and you just don't put any variable in the end. Okay, so it just stops linking at the end. Okay, so some basic, again, definition is the dual of a vector, A check, is defined by just changing just flipping the ordering of these integers. Okay, so for example, for this guy, the second polynomial, the vector will be 2, 7, and its dual will be 7, 2. Okay. So there is a famous conjecture by physicists about these polynomials. So these polynomials are special cases, but maybe 1/2 of all the actually different cases. They're called invertible polynomials. And this kind of switching the order is that I defined. So the polynomial pair PA and PA check are examples of dual invertible polynomials. And if you think of these polynomials as maps from just n-dimensional complex affine space to complex numbers, just as functions, holomorphic functions, these are supposed to be mirrored to each other. I'm going to give a more precise kind of meaning of what it means to be mirrored to each other. But there are many different manifestations of this. Okay, so this conjecture was done in kind of the early 90s. And it was kind of an experimental conjecture, I would say. There is they did some computations and it checked out, but they didn't do a significant, very like, you know, to me, nothing that would say that this conjecture will be true in general. But then a couple of years later, there's some other paper by Berglund and Henningson, also a physicist, and they did some computation. We checked something for all dual invertible polynomials and showed that there's something to it. So even though this is a very simple operation, it seems to actually work very well. Okay, so I kind of said, I mumbled that this is maybe half of the story. So the other half of the story is about loop type polynomials. And maybe you can imagine that loop now would mean that this the linking of these polynomials goes in a loop rather than in a chain. So that means when you get to the end, you connect back to the first variable. So I will just have to add an x1 in this place, and that would be a loop type polynomial. Okay, but the work that I'm going to mention today, we didn't really do anything serious about loop type polynomials, so I didn't really include that in my notation. Okay. So as I mentioned, so this Berglund-Hoops mirror symmetry conjecture has been interpreted differently by different people. And I'm going to focus on one particular interpretation. And it's a homological mirror symmetry conjecture. So it shows that it kind of conjectures that two categories associated to these two polynomials are the same. And this one's due to Takahashi. Okay, so now I wrote this. I mean, I'm talking about some very basic stuff, polynomials, and then I write these very complicated looking categories. Yeah, I mean, unfortunately, that's just how it is. So the category on the left side is what people call A side. So this is supposed to be the side that's more relevant to symplectic geometry. So it's supposed to be about the symplectic geometry of this PA considered as a map from Cn to C. But this is, again, you know, the symplectic geometry here is kind of a soft symplectic geometry. It's yeah, I mean, maybe I shouldn't try to explain more. Okay, and on the B side, it's supposed to be more about kind of complex, I don't want to say algebraic geometry, but at least in terms of the tools and who thinks about that kind of stuff, it's more about complex algebraic geometry. And so the category on the right-hand side, I'm not going to say almost anything about today. So let me just at least tell you what these letters mean. So this HMF stands for the stable category of a matrix factorization category. So this matrix factorization, so this kind of, I mean, roughly we're trying to find matrices that multiply to this polynomial PA check. And these are supposed to be kind of over, everything is supposed to be happening over the ring of polynomial functions. And this L guy is giving you some kind of non-standard grading by some abelian group. So this is an abelian group on this ring. And everything is supposed to respect this grading. So this is also called equivariant matrix factorizations. But it's, in the end, it's some, after you take the stable category, it's some triangulated category. Okay, and on the left-hand side, but at least you see somehow that there is my polynomial somewhere in there. So it's somehow, you're thinking about factorizing that polynomial as a product of two matrices. And these matrices kind of are, I don't know, acting on modules over this ring. If you're interested, maybe you can go, maybe you can read about it. I can give you references. It will just take too long for me to, and I will talk about the A side, and I will mention, maybe I mentioned from now that the computations on both sides, even though somehow we prove the same thing about both sides, they're proved completely separately. So knowing the B side actually doesn't really help the A side. Okay, so on the A side, what we have is the Fukaya-Seidel category. So it's a derived category of the Fukaya-Seidel category of this map PA. And the Fukaya-Seidel category is an A infinity category. I'm going to tell you a little bit more about that later. Okay, and again, this what we have on the left-hand side is also a triangulated category. And what the conjecture is asking for is an exact equivalence between them. And our theorem with Polishchuk is that this theorem is true. It's not yet exactly a theorem because of some completely expected foundational results for Fukaya-Seidel category. So this A side, they're stated everywhere in the literature, but they're not really proved anywhere. So we also have to kind of include proofs of these results. So recently, Maxim Jeffs joined us to also kind of take a role in this part of the project. So it will probably, in the end, be a joint project between me, Polishchuk, and Maxim Jeffs. And as you can guess, Polishchuk, he's an expert on the B side, so the computation on the B side, more or less, he did it by himself. I watched parts of the process, but it's a kind of a complicated, to me at least, computation. In my opinion, what's happening on the A side is more clear. On the B side, somehow we just believe that what I'm saying is true and try to replicate it on the B side, and it worked. Okay, so how do we show this? So again, I'm gonna have to be kind of rough and not really make precise statements. So what we show is that the categories on both sides satisfy some kind of recursion. So we have some, I will not describe this operation just yet, but we define some kind of recursion that takes in some triangulated A infinity category with an exceptional collection, specified a full exceptional collection. Okay, it's a full exceptional collection. Maybe I won't add it. And it also takes the input at sufficiently large integer. The integer basically has to be bigger than the number of elements in this full exceptional collection. And then you apply this operation to it, and that outputs for you another triangulated A infinity category with a longer exceptional collection. Okay, so then what we actually prove is the following statement. So let's define, let's introduce this notation. So this guy over here. So if I put minus A, that means I remove the first entry of this vector. And if I put A minus, then that means I remove the last entry of this vector. And what we prove is that on the A side, the recursion is satisfied in this way. So the category for A is obtained by this recursion from minus A. And on the B side, we show that the same happens from the other side of the vector. So if you want to obtain A, you want to remove the rightmost entry of this vector and apply this recursive procedure. Okay, and then to get the theorem, what we do is you can show that the categories actually can be defined for the empty tuple. And then it's kind of trivial that this homological mirror symmetry holds for this empty tuple. And then just by using this theorem, you can inductively show that the theorem holds for all tuples. Okay, because when you add something to the right on the A side, you add something to the same number to the left on the B side. So you exactly recover this duality between the integer vectors. Okay, and as I already mentioned, the proofs are independent of each other. So I'm not going to tell you anything about the B side. I'm going to try to tell you something about the A side. Okay, so the rest of the talk, I'm going to try to define. I'm not really going to be able to define it, but I'm going to try to give you a flavor of what kind of object this Fukaya-Seidel category is. And also try to explain what this recursion does geometrically. I'll also say what it is in the end, algebraically, but yeah, my goal is to at least try to signal something about how it comes about geometrically. Okay, so now I come to the part of the talk where I'll discuss some basic notions from Picard-Lefschetz theory. So are there any questions? Okay. So Picard-Lefschetz theory is in words. So it's like in Morse theory, you use Morse functions to study the topology of manifolds, smooth manifolds. And in Picard-Lefschetz theory, you use holomorphic Morse functions to study the topology of complex varieties, smooth complex varieties, or you can also talk about analytic manifolds, but let's restrict ourselves to the algebraic case. So, you have the basic situation could be that you have some smooth algebraic variety over complex numbers, and you take some kind of generic function, which happens to have only generic singularities, which are Morse type, which I will tell you what that is now. And then you use this structure of this map to say stuff about the topology of this complex algebraic variety. Or you can also do a similar study for kind of families of algebraic varieties. Okay, but all of this story is based on this local model. So this local model, so it's right here. So it's the map from Cn to C, given by just the sum of the squares of all the variables in Cn. And this guy has just one singularity at the origin. And that singularity at the origin is called a Morse singularity, holomorphic Morse singularity, if you want. And it's the generic singularity for holomorphic functions. So, if you take a generic holomorphic function, it will only have this kind of singularities. And the geometry of this map is kind of as follows. So let's draw the base of this map, like over a disk here. It's the whole complex plane, but I just drew this. And over the origin of the base complex plane, that's where my singularity is. That fiber is where my singularity is contained. And that fiber looks like a singular variety. And for example, you can easily compute what it is in the case when n equals 2. And all pictures are generally in this context drawn for n equals 2, which I will also do the same. So you can see that it's just x1 squared plus x2 squared equals 0. So that factors into two linear functions, and you just get the kind of transverse intersections of two complex planes. Okay, but that I draw as this cone. So you can, if you want, imagine the upper half of the cone is one of the planes, and the lower half of the cone is the other plane, and they intersect at one point. I mean, this cone picture is a little misleading, but this is what traditionally drawn. So what it really is it's two transverse intersecting planes, complex planes at one point. But this is some kind of map. You just represent it by an image of that into the three-dimensional Euclidean space. Okay, so that's what this looks like. So it has a singular point, and there's this one plane here, another plane here. And if you take any other point, then since there's no singularity about it, the fibers are going to be smooth. And they're going to be diffeomorphically, and in fact, symplectomorphically too. I will say that a little bit later. So they're diffeomorphically equal to cotangent bundles of spheres. Okay. So being cotangent bundles of spheres, they have the sphere inside them. And if you take a path downstairs and follow through, you kind of make some kind of coherent choice for these spheres along the way and follow it through, you will see that those spheres will collapse to a point at the end of that path. Okay? So the sphere that's there is a sphere. So this is you can think of it as, if you fix a diffeomorphism, you can take the zero section, but there's more invariant ways of defining it too. So there is a sphere inside any of these regular fibers, and it vanishes as you go from that fiber to the singular fiber. So that's called a vanishing cycle. And there are two ways of there are two levels of thinking about this object. So the first level is the classical level, where you think of that sphere as defining for you a middle dimensional homology class. Okay, so that would be what you would do in classical Picard-Lefschetz theory. And in the symplectic Picard-Lefschetz theory, you think of that as a Lagrangian sphere. Okay, and let me tell you a little bit about what this symplectic structure in this case is. It's a stupid thing. So during this talk, all of the affine varieties that I'll talk about are going to be explicitly embedded in some complex affine space. And this complex affine space has the standard symplectic structure. So the complex plane itself has a symplectic structure. If you write the real part, represent the real part as with the real coordinate x and the imaginary part with the imaginary coordinate y, dx dy for C is a symplectic structure. And then you can equip any finite dimensional complex affine space by the product symplectic structure. So therefore, any smooth submanifold, any symplectic smooth submanifold, in particular holomorphic submanifolds or symplectic, can be equipped with a symplectic structure by just restricting the symplectic structure to that subset, to that submanifold. And that's what I'm doing here. So this fiber has a symplectic structure, and with that symplectic structure, it's stop pointing. Okay, with that symplectic structure, it's symplectomorphic to the cotangent bundle of a sphere. This seems like a choice, but this for an affine variety, smooth complex affine variety, the choice of a symplectic structure is not actually a choice. It's well defined. If you choose a different embedding to a complex affine space, you will get another symplectic form, it seems, but actually the two symplectic forms that you get from two different embeddings can be related to each other by a deformation. So there is, in a certain sense, there's a unique symplectic structure on a smooth complex affine variety, but I'm not going to need that today. Okay, so now let's give the key definition of Picard-Lefschetz theory. So if you have a smooth affine variety over, just over the complex numbers x, and you take a polynomial function, let's say regular function, from x to c, you could take a holomorphic function too. And this is called the Lefschetz vibration if all the critical points of this map pi are holomorphically Morse type. And the Morse type is also called non-degenerate because you can characterize being a Morse singularity by looking at the Hessian at that critical point, and just this quadratic form should be a non-degenerate quadratic form that characterizes being Morse type. And I also make this mild assumption that the critical values associated to two different critical points should be also different. So I don't have two critical points lying on the same fiber. Okay. So now let's go through this some of this terminology. So okay, so I have this base now. I just started drawing the base. So I will always denote the critical values by x's on this base. Okay, so that's the first definition. And then a second, a vanishing path is a path that goes from a regular point, a point with a smooth fiber, to a singular point. So a critical value, so that fiber above it is a singular fiber. Okay, so that's a vanishing path. And for every vanishing path, I can construct a Lefschetz symbol, which is this. So that's basically the picture from the local model, like this. But now the path, so locally, by assumption, what I have above this point looks like that local model. And if I take a longer path that doesn't lie in that local model, I have to use some kind of parallel transport argument to carry this vanishing cycle all along this path. Okay, so this gives me, again, you can think of this Lefschetz, so this Lefschetz symbol lives in the total space in X. And again, you can think of it in two different ways. Well, the first one, you can think of it as a relative homology class. So it's a member, it's an element of the homology relative to the fiber above this green point. Okay. So again, that would be the classical Picard-Lefschetz theory. And in symplectic one, you think of this as a Lagrangian disk or n-dimensional disk or a ball, maybe it's better to say. And finally, the the end point of this Lefschetz symbol at our fixed green regular point is called a vanishing cycle. Okay, and I'll give one last definition. And again, let's take some Lefschetz vibration as before. Again, I have my critical points, critical values living in the base. And now I take a path going between two of these critical values. And not all such paths are good for me. I will call I will call a path that satisfies a property a matching path. Okay, and the property is the following. So let's choose an arbitrary regular point along this path. And I can consider the Lefschetz symbol above the left side of this path from my critical value until the point that I reach the regular value that I fixed. Okay, so here we go. That's one Lefschetz symbol. It's living in the total space. And I can do the same thing from the right. Okay. So this way I obtain two vanishing cycles in my green regular fiber. Okay. And there is no reason why these two vanishing cycles should have any relation to each other whatsoever. But if it happens that they are homologous in this fiber, in the classical case, or in the symplectic case, if they're Lagrangian isotopic, so if there's a one parameter family of Lagrangians that starts with the first one and ends at the second one, then I will call this a matching path. In fact, in practice, if the homologous happens, generally the second one is the reason why they're homologous. So there is, I mean, you might be asking me, so then do you want to define two different kinds of matching paths? I don't actually have to in practice. So that's the definition of a matching path. And the last definition I wanted to say is the definition of a matching cycle or a matching sphere. And this is now in the total space. So if it's a matching cycle in the total space, it's actually a homology class of the middle dimensional homology of the total space. It's not a relative homology class anymore. And how is it constructed? Well, I fix my two symbols, and I'm given that they're homologous, for example. And then, well, that means in practice that you can choose you can choose a cycle with boundaries, with kind of, with boundary that composes of this kind of the union of the two vanishing cycles that I fixed. That's what it means to be homologous. So then you just take the union of the two Lefschetz symbols and that cycle. And if you just take the union of these three things, you get a cycle in the total space. And if you have a Lagrangian isotopy, then this symbol is a Lagrangian ball. The other symbol is also a Lagrangian ball. So you have this kind of singular looking Lagrangian object. So you have to kind of massage that a little bit to actually get a Lagrangian, but it can be done. Okay, so this is all I have to say about kind of basic definitions in Picard-Lefschetz theory. Any questions about this? Okay.
No.
So now let's go back to our chain type polynomial. So this chain type polynomial, you can easily see that it has only one critical point at the origin. But this critical point is unlike the Morse type singular point that I've been talking about. It's a degenerate singular point. Okay, so it's a much more complicated, there's something much more complicated happening at this point. Okay, so now let me first define the classical version of the Fukaya-Seidel category. So this is defined as a non-symmetric pairing on this relative homology class. Okay, so the relative homology group. So this is maybe a picture is better. So I have my vibration. I have my map from Cn to C given by PA. I restrict this to some disk. It's not important how big this disk is and all that stuff. And on the boundary of this disk, let me take the unit disk. And on the boundary of this disk, I have just the complex number 1. so I look at the relative homology group, which is just the pre-image of this disk. So this is a homotopy equivalent to just the total space of this vibration, to Cn. But I look at it relative to the fiber at this 0.1. And note that 0.1 is a smooth, it's not a critical value. So the fiber above it is just a regular fiber, a smooth fiber. Okay, so now, so this is the kind of abelian group. And on this abelian group, there exists a pairing, which is called the Cypher pairing, and it's non-symmetric. Okay, so how is that defined? So we can first take a diffeomorphism of the base disk, which does the following. So it's in a small disk, its identity. And I want it to be a very small rotation, kind of at the boundary of this disk, let's say counterclockwise rotation. So I start at identity, and then I slowly interpolate between that small rotation and the identity. Okay, so the points in the boundary rotate just a little bit. If you go a little bit inwards, then you rotate even smaller, and then at some point you stop rotating at all. Okay, and then by using kind of parallel transport arguments, you can lift this to a diffeomorphism of the total space, which is Cn in this case. Okay, so let's take this. So the lift takes, for example, the fiber here to the fiber here, right? So that it maps that the diffeomorphism phi maps the fiber at 1 to the slightly rotated fiber. Okay, so now if you take two elements of this relative homology class and you want to define its pairing, so this is supposed to be a number. Now what you do is the following: you take E, you take the first of these homology classes, and you move it to the fiber that's slightly rotated fiber using my diffeomorphism. Okay, so you can do that. The boundary of this homology class, it used to be on this fiber, but now that I applied my diffeomorphism, its boundary is now on this fiber. Okay, so now I have this relative homology class and this relative homology class, and their boundaries are contained in different kind of disjoint fibers. So now you can actually define a homological pairing of these two classes. Okay, so this is a general kind of cup product type pairing. Okay, I will kind of, so this is a very general definition, and it's not as geometric as you would like it to be. It will become a little bit more geometric soon. Yeah, I mean, I said cup product, but probably like a better way, maybe that's too confusing. I should just say, like, if you have a closed even dimensional manifold or something, then you can look at if you have middle dimensional submanifolds, let's say, in that manifold, then you can look at the intersection number between these two manifolds, two submanifolds. So that's what I'm doing here. Any questions about this? Okay. And of course, you notice that this definition is a lot more general than just for the map given by the chain type invertible polynomial. And I won't try to say how general it is, but you can guess it. And now the question is, okay, you define this, but now how do you actually compute it? And to compute it, then actually that's where the Picard-Lefschetz theory comes in. So what you do first is to take this polynomial and you perturb it to a Lefschetz vibration by adding some new polynomial, small polynomial to it. And then you can use Picard-Lefschetz theory. So in this case, what we do concretely is to do the following perturbation. So we start with PA. So this is the polynomial that I defined in the beginning. And you just added some epsilon can be taken to be 1 here. You just added some multiple of the first coordinate function. Okay, and then when you do this, so this PA considered as a map from Cn to C had just one singularity. And once you turn on this perturbation, you will see that this explodes into multiple non-degenerate Morse type singularities. Okay, so this mu A is the number that you can explicitly compute. It's called the Milnor number. And I mean, you can explicitly compute it in this case for PA. And in general, it's called the Milnor number. So how many non-degenerate singularities this explodes into is some measure of how complicated the original singularity was. Okay, so now let me draw what happened, not for critical points, but for critical values. Okay, so in the base of PA, the map PA, I had just one very complicated singularity at the origin. And now these guys explode, that kind of fat singularity exploded into some simple singularities. And for this particular perturbation, it happens to be the case that they're placed on a circle, and they're placed kind of regularly along this circle. So the angle difference between adjacent ones are the same for all of them. And you know, there are Milnor number many of these critical values. Okay, but now
I have a question.
Yes.
So,
yes.
is there any specific reason that you chose that deformation of the polynomial?
There is. Maybe I can tell you after the talk.
Okay.
There is. Yes. I mean, you could choose any random perturbation, and this explosion thing would happen. But of course, then you would lose some of the structure. So I'm choosing a particular perturbation that keeps some of the structure that this original polynomial has. Yeah, that's a good question.
Okay.
Okay, but now that I perturbed and I obtained this Morse type singularities, now I can actually construct some elements of this relative homology group, which are given by Lefschetz symbols. Okay, so from each of these critical points, I can just take a path which doesn't intersect. It's an embedded path, and it doesn't intersect any of the other critical values, and it ends at a regular point, and it ends at this green point. And to that, I can associate a relative homology cycle given by the Lefschetz symbol. And moreover, I can actually take what's called a distinguished collection of vanishing paths. So what this means is you take one path from each of the critical values to the fixed regular value, and so one from each, and they're also not supposed to intersect other than this regular fiber. So they're only going to intersect at the green point. There are many choices for this. I gave you one particular choice. You could choose any other. And the fact is that if you look at the homology classes in the relative homology classes that you get, then you have the Milnor number many relative homology classes. This gives you a basis of the relative homology group that I told you about. So if you wanted to compute the pairing, for example, you could just compute it on this basis. That would determine it. Okay, and another point that I want to make is that if you are trying to compute this intersection number, kind of non-symmetric intersection number between two thimbles, then that's actually just, let's consider these two thimbles, for example. What you're really computing is the intersection number of the vanishing cycle inside the vanishing cycles inside the green fiber. Okay, let me make that a slightly more rigorous. So now let's take let's try to compute the Cypher pairing of two thimbles. Okay, so the first thimble I call E and the second thimble I call F, and they're given by these two orange paths. Okay, so try to ignore the rest of the picture. Okay, so let me first try to compute, because it's easier, let me try to compute F intersection E. So we have this guy and this guy. And what you're supposed to do is that you're supposed to move this thimble a little bit counterclockwise to another thimble. That's just how the intersection was defined. But once you do that, you see that there's actually no more intersection between F and E. Okay, so the F is this and E is this. So they just don't intersect. So this intersection number is 0. But if you try to compute it in the other direction, if you do E intersection F, And what you're doing is moving E slightly counterclockwise, and F stays the same. And now they actually intersect at this point that I think marked in brown. And it's easy to believe that this intersection of the vanishing cycles inside the brown is the same as the intersection in the green fiber, intersection of the vanishing cycles in the green fiber. This is not supposed to be here. Sorry about that. Yeah, that was just not supposed to be there. It's a typo. Okay, so this is my explanation for what Cypher pairing is. So any questions?
What does this correspond to in the B side, in the singularity category?
It's the Grothendieck group with the Euler pairing.
I see. Okay. Yeah. Thank you.
Yeah. So I mean, just in line with this answer, the Fukaya-Seidel category is a categorification of this relative homology group with the Cypher pairing. I'm not going to give you a full definition. I'm just going to tell you what the objects are. And there are, again, various flavors of this, and I'm simplifying, and it's a complicated technical subject. And as I said, there are some properties that this category is supposed to satisfy, and these are not exactly checked in the literature. Okay, so the objects of this category are actually Lagrangians now. And these are Lagrangians in the total space. So I'm again restricting to this PA story. And they're supposed to be Lagrangians that look like a thimble of this orange path. So it's not really a thimble, but just the Lagrangian living over this orange path. So you just take the union of the vanishing cycles of each point on this orange path. So it's supposed to look like that at infinity. And inside a compact set, it can be whatever it wants to be. And again, there are different flavors of this. But this captures, I think, what it's trying to do. And this condition is kind of like being a relative homology class. Okay, so requiring it to look like this is the same as requiring a relative, like that you have a relative homology class where it's relative to a fiber. Kind of it's reminiscent of that. So you have all this is an A infinity category, this Fukaya-Seidel category. If you don't know what that is, it's not that important for the talk. And its objects are these Lagrangians, and its morphisms are now, so you know, a categorification, you upgrade a vector space to a category, and the morphisms now, you know, the numbers that were so there's this vector space has a pairing, and that's given by a bunch of numbers, and those numbers are supposed to be turned into vector spaces, which are the morphisms between different objects in this categorification. So now morphisms between two such Lagrangians are given by, again, a similar procedure to this kind of slightly moving one of them slightly counterclockwise, which I will just say in quotation marks infinitesimal rapid. And there's this entire theory of Floer homology for Lagrangians. So what that does for you, it gives you a chain complex. So it's it's generated by the intersection points of the two Lagrangians, and there's some differential on it, which is defined by counting some solutions of the Floer equation. And then to define compositions, or in this case, multi-compositions, because it's supposed to be an A infinity category, you count more solutions of Floer type equations. Okay, so giving a real definition of this would take too long. And somehow one of the points in this computation is that you don't actually really need to know how the category is constructed. You're supposed to know some properties that it satisfies. So like the proof on the A side doesn't actually compute a single Floer solution. It just uses general properties. Okay, so now let me somehow try to tell you a little bit about how, like, what you actually get when you try to run these things in PA. So let's introduce another general notation. So if I have any kind of affine variety in Cn, then it's I can project it down to complex plane using the first coordinate. Let's call that projection sub 1. So okay, let's say we were interested in computing the ciphered form for this chain type polynomial. Okay, so I already told you that you can perturb it and you will see these regularly placed critical values that lie on a circle. And I also told you that I could just compute the pairing on some distinguished basis of vanishing cycles. So I choose this particular distinguished basis of vanishing paths. Sorry, I think I said cycles. Distinguished collection of vanishing paths, so they don't intersect in the interior, and there's one from each of the critical points. So you start with one of them, it rotates like this. Okay. And then I commented to you that to compute these intersection numbers, then it's basically about computing the intersection numbers of the vanishing cycles inside the green fiber. So now to analyze that, what I'm going to do is to take another Lefschetz vibration on this green fiber, which is given by this projection 1 to complex numbers. And then if you analyze that, you will see that again, somehow roughly all the critical values lie on a circle and they're kind of regularly placed. So you can do all of these computations in a computer. You can also prove them. So the way you do it, you generally first do it in a computer and then you prove them. Yeah, and then, so now kind of the part of this whole story that's most fun to me is this, this following step. So in this situation, there's a general algorithm to compute the vanishing cycles at this green fiber as matching cycles using this one, for example, this Lefschetz vibration. Okay, so let me just tell you the result. The result is that each of these, so let's take this one, for example, its vanishing cycle on the green fiber is given by the matching cycle of this matching path. Okay, so there are two statements there. One is that this is actually a matching path and that it has a matching cycle above it. And that matching cycle is the vanishing cycle of this path. Okay. And you know, it's kind of nice as you rotate these paths counterclockwise, you get kind of counterclockwise rotations of this, these kind of, I call these petals, let's call them petals. It's like flower petals. So you get these petals. Okay. And then now, in order to, you're supposed to now understand the intersection properties of these matching cycles. And then you need to find a way to continue going down in dimension. Okay, so you need to find a way to actually compute these. So now each of these intersections happen in a fiber that's one dimension lower. You have to find a way to get in there. And I'm not going to explain this to you, but I did this. I mean, it's not, that part is not really algorithmic. There is some kind of some kind of geometric idea there. But by kind of following this through, I can confirm some conjecture by Orlik and Randall, who just kind of analyzed these chain type singularities before any of this mirror symmetry story. And they just kind of, they did some computations. They computed what's called the monodromy of the singularity. And they made a conjecture about what the Cypher pairing should be. And they were right. And I checked that they were right using this strategy. But what I wanted to really kind of point out in this case is just this part. Is this kind of dimensional reduction. If you're trying to analyze these kind of n-dimensional objects, you go down and you reduce to analyzing these n-1 dimensional objects, and hopefully you can continue this path and get something inductive. Okay, but what you have to do for the Fukaya-Seidel category is a little more involved. So again, let's go back to the base of this perturbed polynomial. Okay, so I have these intersection. So I'm going to start calling this intersection numbers or flirt here. I'm going to start calling it intersection information. Okay, so it's vague, but so I need to compute. I still want to compute the intersection information of these orange paths, but now I want to compute more. I want to compute the Floer homology groups and products and all that stuff, not just intersection numbers. So in order to do that, I actually want to compute the intersection information for a different choice of distinguished paths. These distinguished paths are called dual, are what's called a dual distinguished path. So if you imagine just dragging this this point, this origin point, out towards the green point, and just dragging all the blue paths along with it, such configurations of orange and blue paths are called dual paths. And the properties that, you know, the kind of the intersection information for one can be obtained from the intersection information of the other by some purely algebraic operation. Okay, and to use more of the symmetry, I actually want to compute the intersection information of the blue paths, not outside at this green point, but inside at the origin point. So I just drew the end of that reasoning. So now I want to, you know, upshot is that now I want to compute the vanishing cycles inside this orange path. Inside this fiber about the origin, which I think is purple. So the purple fiber, or blue maybe. Well, anyways, so the vanishing cycles are going to be drawn in blue. So now you have to do some more perturbations. You will see that if you just take this this fiber at the origin and do the projection one, that's not actually a Lefschetz fibration. That has a fat singularity at the origin, and that fat singularity at the origin is actually exactly the same singularity that you get by doing this minus A. And that's kind of the base of this induction. But what you do is you do some further perturbations, and then you can draw the vanishing cycles as the following matching paths. So you draw this one first, and then at each step, the outside, so there's now kind of, there's this interior circle and the outside circle. And each of the matching paths will go from the inside circle to the outside circle. And the first one is just this one that aligns with the positive real axis. And each one, starting from this one, the next one is considered is obtained by moving the endpoint out endpoint counterclockwise and the in endpoint clockwise. Okay, so I start with this, I go this way, and I obtain this. And then I keep doing this. So I move this one here, so now it's going like this, and this one here, it's like this. And if I were to draw the next one, it would look more complicated. It would look kind of, I don't know if I'm going to be able to finish this. Yes, actually like this. I don't know if you were able to follow it, but it's this kind of nice configuration where they just rotate by once outside and rotate by once inside. And the kind of a slightly more refined version of what I just said is that if you look at a disk, like a yellow disk like this, what you're seeing inside is well, not exactly, but up to some deformation, is the picture that you would see in one dimension lower if you were to kind of use the Lefschetz fibration that you obtain by perturbing P minus A. Okay. Yeah, so now let's kind of go back to the base of P minus A, the perturbed version of P minus A. So X1 is gone with the P minus A. And now in that dimension, so I'm gonna now get something inductive. So let's assume that I know the intersection information of this distinguished collection that I had chosen. So now the point is that if you know the whole intersection information of this, then you actually know the intersection information for a much larger class of thimbles, which are obtained in the following way. So you just fix one of the critical values, and you kind of go outside of this kind of imaginary circle. You rotate as many times as you want and align with the positive real axis. So that's a lot more. So these are all examples of that, but there's a lot more. And all the intersection information of those can be again kind of algebraically determined from just these distinguished collection. Okay. And so now if you look back here, if you look at what you're seeing inside the yellow circle, what you're seeing is, and there's like 5 of them. So each of these 5 guys actually look a lot like this kind of vanishing path. And there's a way to make that precise. So like now we're computing intersection properties of these blue paths, but all the intersections are happening inside the yellow disk. And if you were computing some Floer trajectories, etc., there's some open mapping principle that lets you prove that those guys also don't go out of this yellow disk. So this kind of computation of the intersection information for this blue path actually can be done by just the information that stays inside this yellow disk. And the information that stays inside the yellow disk is basically the information of these can be recovered from the intersection of this kind of vanishing paths in 1 dimension lower. So that means that we can compute the intersection information of the blue vanishing cycles from the orange symbols of 1 dimension lower. Okay, so this is how you get a recursion. And let me just end by saying how the algebraic recursion looks like. So you start with some triangulated infinity category and some exceptional collection. So, I mean, and this is for the experts. I'm not going to try to define everything. So there is what's called a helix with foundation given by this exceptional collection. So that's an infinite collection of objects of this category. And now you have this, you choose this number mu bigger than mu minus, and take mu adjacent elements in this helix, and you make it directed. You just remove the morphisms that go in the wrong direction. And that defines for you another, so you just take that subcategory, and that subcategory by definition has an exceptional collection. And then the final step is you take this triangulated infinity category, you take its twisted complexes, its triangulated closure, and take the dual exceptional collection inside that triangulated closure. And this is kind of the recursion. I mean, this is like, there's some issues with, not issues, but you have to say something more about the gradings and stuff. I just gave you some most basic version of it. Okay, I think this is all.
Thank you. Let's thank Umut with the reactions on the chat. Or do you have any questions for Umut today? Anyone?
Well, maybe you made a couple of deformations of your original polynomial. And how do they preserve the intersection information? I kind of like.
Oh, it's so that's because these perturbations are very small. So you can just parallel transport everything. Like it's just everything's changing just by very little amount and continuously.
Okay.
Okay, I mean that's the basic idea. Say more, you have to actually write.
No, when you take epsilon 1, I thought like maybe you are making arbitrary large deformations, and it's still
it's not supposed to be large. Just in this case, this is so this invertible polynomials and the perturbation that I'm using are both what's called tame. So they are very, very well behaved at infinity. So you don't have to make it very small in that case. Normally you would need to know, if you're dealing with an arbitrary singularity, complex isolated singularity, you have to take a small ball where you have to localize to the information near the singularity. And you have to really take the perturbations very small so that all the fibers still kind of stay transverse to the boundary of that ball that you fixed. So this is what's called Milnor fiber, and like the story gets more complicated if you're talking about a general singularity. But in this case, these are very well behaved. You have to prove that, but they are. So it doesn't have to be small in this case, but in general, it has to be small.
Also, I asked another question and you said you
yeah. So that question. So this invertible polynomial is what's called a quasi-homogeneous polynomial. So there's a action of C star on Cn. So which is a diagonal action. So you multiply kind of each of the variables by some number. So so let's call the parameter of C star t. So you multiply each of them by t to the some power, and resulting the result of this kind of if you just put, instead of x you put t to the some fixed power times x, and you write it down, and then what you get in the end is t to the some other power times the polynomial that we started with. It's like homogeneous polynomials where if you multiply all the variables by t, then you would just get out t to the degree of that polynomial, right? But this is quasi-homogeneous. Okay, a geometric way to think about this is that so there's this map, you consider this polynomial as a map, and there's an action of C star in the total space, and there's an action of C star on the base, and this map is equivariant. Okay, so the base is rotating if you look at the rotational part of the C star, and kind of scaling, you look at the real part of the C star. Okay, so this is a symmetry of this polynomial, and this polynomial, so now I want to perturb this map, right? So if I perturb it any old way, this equivariance will be destroyed. But this perturbation that I do keeps, there is a kind of a subgroup of this, the finite cyclic subgroup of C star, and it's a cyclic of order Milnor number. And I told you that this kind of, after I do this perturbation, you get kind of this regularly placed points on the circle, right? So the real reason for that is that that cyclic symmetry is preserved after I do this perturbation. So there is an action of the cyclic group of order mu, which rotates the base by the standard rotation action. So there's the entire picture is symmetric. And that's why you're seeing that regularly placed configuration. But this preservation of symmetry will not hold for anything other than this perturbation. So that's why this perturbation is special.
Okay. Thank you.
Mm-hmm.
Any other questions? More comments? I am curious about the endomorphism algebra of this exceptional collection, and how do...
Yes, one point about our proof is that we don't compute that.
No. But without the computation, without the computation, for instance, what does this R do? Can you describe that action of R on the endomorphism algebra without knowing what it is?
So I can give you an example. For example, you can start with the category of vector spaces over a field, and this has an exceptional collection just consisting of one object. Okay. And then if you do this helix extension, what it does is this infinite sequence is just a repetition of that object. Okay, so you have this kind of infinitely many objects, and between each of them there's just a one-dimensional morphism space. And then you truncate this. Okay, you just take a truncated kind of and many of them, adjacent ones, and then remove the morphisms that go in the wrong direction. So now everything is going from left to right. And now I'm supposed to take the dual. When you take the dual, what you get is exactly the AN quiver. If you've seen this before, so the left dual collection of the standard one for the AN quiver is this one with a lot of intersections. This one where you can compute. And I mean, that's one example. The AN quiver where the morphisms have degree 1. So the compositions are going to be all 0. So that category just looks like some objects and some one-dimensional morphisms all in degree 1, just between the adjacent ones and no other morphisms. Okay. And it gets more and more complicated. Like if you do it more, then you actually have higher products.
Mm-hmm.
So we computed it for maybe n equals 3. We computed it too. It just becomes too. There's a lot of higher products. This is kind of not the most economic representation of these categories.
Mm-hmm.
But it's just one that that you can prove geometrically. Okay. I mean, these categories are supposed to, for example, admit strong exceptional collections, I think. These are definitely not going to be strong. There's going to be a lot of morphisms in different degrees and a lot of higher products and things like that.
I see. Thank you. And if no more questions, we can say thank you again to Umut.
Thank you.
So next week we have